Sir, you can start, sir. We are live.
Okay, Vignesh, thank you. So good evening to everyone. So today we have Professor Arun Rajkumar sir from IIT Madras with us. You can ask any questions related to his contents, week 7, 8, 9, regarding optimization and convex function and properties.
Thanks, Amrita, and thanks, folks, for joining. You can ask questions about anything in general also. If you have any general questions about the program, the contents, not just optimization, even if you have something about other things that you have seen also, we can discuss. I mean, if I can, I'll answer them as well.
Yeah, so you can raise your hands, participants, if you have queries.
So how many are participants here? Around 4, right?
So there are 6 participants.
6 participants, okay.
Yeah. And sir, for updation, this is 12th week, which is live now.
Sure.
So 7, 8, 9 week is already covered, and people have already attempted quiz 3.
Okay.
Which had questions of your weeks. And up to week 9.
And I guess the tutorial session is also complete, right? So for week.
Yeah. Yes, sir. So anyone having any questions, please ask it. It's a very nice opportunity for all of you.
Or if you have any comments, general comments about the program, the topics covered, anything is fine, right? So I think the goal is for me also to understand how the participants have felt about the program. What are some areas of improvement, if any, so that for the next batch we can focus on and so on. Feel free to discuss anything. I mean, yeah. So if there are only a couple of participants, right? So maybe we can go over a round of introduction so that I've never met any of you. Can we go over a round of introductions with the participants?
Yeah, sir.
Sure. I don't know who are the participants here. So maybe Abhinandan, if you can help me pick people here so that they can unmute and introduce themselves.
Yeah, sir. Sure. So Ayush, can you hear us?
Ayush, if you're speaking, you're muted.
So Ganesh Lakshman. So if you have any queries, you may also type in the chat box. Sandeep.
Sandeep disappeared.
So Srinivasan sir is there. I mean, he is one of our course takers only, but Srinivasan sir. I don't know. People are reluctant today.
Okay.
So I missed the question. What was the question?
Yeah, so we have Arun Rajkumar sir with us.
Professor, yeah.
So if he wants to have a general round of introduction, so you may please introduce yourself.
So I've not met any of.
Okay.
So I thought I just have a round of introduction so that I also get to know.
Okay. So usually I kind of whenever I go, my people assume that I've come to drop my kids off for the exam. So nobody thinks that I am writing the exam. So they always ask. So I'm Srinivasan. I have now in the diploma part, and I've actually worked in the software industry. and I have completed that. Now I am on a second career. So I work as a financial advisor.
Great.
And I always wanted to learn, from Python, from data sciences and all the stuff. I want to see how that helps my current work. And in software, I was working on operating system. So nothing to do with this new parts, right? It is all C, and it was working in Unix. So considered boring now. So I find this quite useful. And, so obviously math 1 and 2 were one part, but definitely the MLF, and I think we build on this in the next 2 courses. So I'm looking forward to the other 2 courses also. So.
Great to see. I mean, we don't get to see learners like you in our day-to-day teaching. So great to see. Thank you. Thanks for the introduction. So anybody else who wants to go? Shantanu Ghosh.
Yeah, hello, Arun sir. Good evening. So, just to introduce myself. So, I am Shantanu Ghosh, and I am currently working in IBM. So, for almost in this industry for almost last 16 to 17 years now. Okay, so I have been working on different, POC small projects in and around machine learning, because I heavily work in the SAP practice area for our organization. So what I thought, it has always been a mystery for me to know the mechanics of all the things that people are applying, and many of them kind of always ask me, why do you need to learn so much of mathematics, right? And then I never had the actual answer. I said it is definitely used somewhere, and probably all the algorithms everywhere that you see, you are just kind of scratching the surface, as IITM says, right? So it was all the more intriguing for me to know for it, because typically in the organization where I work, we do serve customers. At the same time, we have a research division. We do have our own suite of products which are heavily invested in AI and machine learning. So IBM is largely focused. So I thought this is the greatest opportunity for me to learn. And given the pace and given the excellent faculty that we have, hats off to you guys. You are doing a brilliant job in teaching us very deep concepts, at least to me. I do belong to an engineering background, but things, for example, that I have learned from the optimization lectures, they're just amazing. Now I can easily correlate what I was loosely implementing these days and what is actually going on behind. So thank you. So
thank you. Thanks, Shantanu. We know the answer for why math is needed in machine learning.
True. Many people still ask, and now I can give them the answer.
Good. Thank you. Thanks for the introduction. Anybody else who wants to?
I can see Rohit. He has opened his video.
Hello, am I audible?
Yeah.
Yes.
Good evening, sir. Myself Rohit Singh. So currently I am only pursuing this degree. So sir, the way you taught the part, that was very nice. So
tell me about what you do and what.
So sir, I had to drop out. I was enrolled in Delhi University, mathematics honors. So I had to drop out due to family problems. Then I joined this degree last year, and as of now, I am only pursuing this degree.
Excellent.
Yeah. So sir, the way you thought was very nice. So actually, sir, I was not aware of the session. I just saw it, and I then went to the forums, and somehow I found the Zoom link, because I wanted to. So sir, that primal and dual problem, I don't think that I have got the intuition for what we are doing there and why we are converting primal to dual and stuff. So okay. If you can clarify or.
Sure. I'll clarify that. Maybe after having a quick introduction, I'll clarify why that might be an interesting.
Sure.
Yeah. Thanks for coming from space and talking to us. Thank you. Yeah. Anybody?
Vikram.
Hello, sir. You may not know us, but we know you because we've been seeing you for the past 4 weeks per se. Day out. My name is Vikram Manath. I graduated last year from a college in Mumbai called as KJ Somaya, Engineering in Electronics and Telecommunication. I'm right now working in Larsen and Toubro Infotech as a consultant in the SAP domain.
Nice.
I joined this program and worked together at the same time. Putting the two together, which is very new in India. I don't think I don't know anyone else who is doing something like this, but I'm really enjoying the course, sir. I am finding it very rigorous, but very fulfilling also at the same time. Thank you very much, sir, for giving your valuable teaching. I find some concepts, I mean, I understand what we are doing, but the intuition behind it is still, I think we'll get to that in the machine learning theory and practice. That's what all the TAs have been telling us, but we have got the math around it. We know what we are doing, but the intuition is something that is still, I am finding it a little here, especially.
Is there any specific module where the intuition is lacking, or is it in general, you're saying?
No. At least for me, the first 4 weeks was all good because I had done that also, and even the last 3 weeks are fine. But for me, PCA concepts are also relatively okay. I mean, it's not like it's completely lacking. It's just not. It is 100% clear. That's the only thing. It's just we just want it to be extremely clear in our heads. That's all. But apart from that, we have gotten the grasp of it. It's just that it's not 100% clear. That's one of the things.
Okay, so I'll talk a bit about PCA as well after this, maybe. Yeah, so I think that is it's very important to understand PCA well, because a lot of later algorithms that you will see will need this as a pre-processing step. I'll talk a bit about this maybe after we'll hear from everybody else. Thanks, Vikram. Yeah. Anybody else around?
Yeah, so there are people. Ganesh Lakshman, I have. Can you now hear us? Or are you?
I don't see Ganesh.
Ganesh Lakshman is not here. I mean,
I guess we've gone for everybody, right? So I don't see.
Shantanu Kush, maybe. No, we talked to him. Yeah.
Yeah. Okay, so maybe then I'll talk a bit about, more like without getting too much into the math part of this, right? So, yeah. So
Srinivasan, sorry, before you start, I would think
yes.
I want to thank, of course, you definitely as a professor, but definitely the team of TS, right? They have been stupendous in this course, right? And I can definitely talk the most about it because there have been many sessions where I have been the only person, right? And then I used to, then others said that they're probably not able to watch it live, but they watch the recording. But we have taken it so correctly, and with the amount of care required, it has been extremely useful. So those sessions have definitely helped. Of course, not to say anything about the lectures, but you need to have the combination, right? You understand when you try to work out, then you realize that, oh, this is something that you didn't guess. I definitely want to thank the TS. I've done that privately with them, but definitely want to do that in front of you. I thank the team. They've done a stupendous job. Yeah.
Thanks, Srinivasan, for bringing that up. I would like to thank them personally on my behalf, and also on behalf of Bharat. I'm sure on behalf of other instructors as well. So we have just done the lecturing, right? So everything else the TAs have taken care of, right? So they have scheduled meetings with us, made sure we go through each and every questions that are given to you as assignments or your final exam questions. Our effort in that has been only 10%. 90% of the effort has been from the TA. So on behalf of all the faculty who have been teaching, big thank you to all the TAs. If all of you had been in a physical space, we would have gone for a treat. But unfortunately, that's not possible now. Maybe we'll do it sometime. Thanks.
Yeah, thanks for the encouragement, sir. And thank you, Srinivasan, sir.
Yeah, thank you, sir. Thank you, both of you, for mentioning us.
Okay.
Yeah, we also loved interacting with you people.
Sorry, I missed that.
About students, I was asking, we also loved interacting with these people.
Sure, yeah. We have, I think, one more student.
Yeah, Shreya.
Hi.
So we just are going over a round of introductions. If you want to introduce yourself and have any thoughts or comments about these general sessions, or if you have any questions, you can ask them.
Oh, okay, great. Hi, I'm Shreya. I'm a chartered accountant, and I'm pursuing this course out of passion. So that's a brief introduction about myself. And so I'd like to really thank you for all of the visualizations and proofs that you've given in the lectures. I found it really easy to follow and understand. And of course, a big thank you to the course support team who's who's very very prompt in answering all of our queries on discourse. And I don't think there's anything that's left unattended to. So yeah, that's been great.
Thank you. Thanks, Shreya, for the introduction. I mean, it's great to see so many different type of people from different types of backgrounds, right? So that's both a challenge for us when we teach, because sometimes as faculty we get to, think that it's important to do it so rigorously that we actually miss, giving the intuition, and because we're used to some kind of audience, and that typically sometimes happens. And so it's important to keep the audience in mind, and that's why I wanted a brief round of introduction as well from all of you. Okay, so I heard two main questions. One was about PCA, what's the intuition behind PCA, and the second is about why care about duality, what's the benefit of solving a dual program. Again, we can go into the mathematical details, but so let's keep that aside for the moment, right? So let's try to understand this more intuitively. Let me maybe first talk about PCA, and though I did not do PCA in this course, nevertheless, you're going to again perhaps see this in the ML Machine Learning Foundations course as well, right? So the simplest way I can think of, I think of PCA. Of course, PCA is a dimensionality reduction technique and all that. It finds some subspace which is good in some sense, and so on. The way I like to think about PCA, or even in general machine learning algorithms, is slightly different from the conventional view, I would say. I would think of these as from the lens of compression, right? So, so how many of us know who's Kolmogorov? How many of us have heard about Kolmogorov here? Okay, Kolmogorov was a great Russian mathematician who actually laid down the axioms of probability. Right? So probability itself was, to give some historical story, right? So probability itself was not on very formal grounds for a very long time. I think right from the time of Laplace and so on, people were trying to understand how to win a gambling game, right? So that's where the notions of probabilities are of most interest, and even so there's a nice book called Men of Mathematics. I mean, all of you should definitely read that, and it talks about a lot of mathematicians and their story, their life story, and so on. So there is one thing about Laplace where he writes a letter about what he thinks is probability and so on, where he says probability is just the calculus of common sense, and that's the kind of that's where it starts, and people were still struggling to understand more formal terms, and Kolmogorov later came on in the 1900s and put probability in a very formal footing, which perhaps you might have seen in the probability classes in I think the weeks after I taught, right? So the axioms of probability and so on. Okay, so this is not about, the story is not about probability, but about Kolmogorov. I think, so he famously said that all learning is compression, right? So you learn really something well if you can compress that information in most, I mean, you can compress it as much as possible, right? So this is something that this quote is attributed to him. And this is a quote, which is fine. But then now we ask the same question for machines, right? So what does it mean to say a machine learns? And the way I would like to think of it is that we are going to think of learning as, understanding something from data And what does understanding mean? And I would take the viewpoint that understanding is in some sense compression, right? So what does it mean to say you can compress information? Let's say you have a lot of data, and somehow I'm going to only retain a few things about this data, which means that I've compressed this data. And now with these few things, if I'm again able to, reconstruct the entire data, you can say that I've kind of compressed this data, right? So now, oftentimes you're going to have data with noise, which means that you will not be able to do like a lossless compression, but still you can get a lossy compression, right? So, and you somehow have to compress it, but then you can lose some information when you reconstruct it, but then you don't want to lose too much, right? So now in some sense, we can think of PCA as simply doing compression, right? So you have a bunch of data points. So let's say each data point is in some D dimension. Now I am going to only store K numbers instead of D numbers to represent each data points. I'm simply going to store only K numbers to represent each data points, where K is much, much less than D. Think of D as say 10,000, but then K is only 100 or 10, right? So which means that you have gotten like a 10,000 by 10, right? It's a factor of compression. Now, of course, the way I have to retain these information is that such that if I again go back and reconstruct the data, I should reconstruct the original as much as possible, right? So I should not really lose anything by doing this reconstruction. So now the question then comes that when can you really compress data? Intuitively, let's say we are in 3-dimensional space and your data is all spread over everywhere in the 3-dimensional space. If your data is everywhere around, then there is no structure. On the other hand, let's say all the data is on the floor. It's all the data points are on the floor. So then intuitively it means that there is some structure here, which means that I can actually compress the data, which means that I don't need 3 numbers to represent this data. I only need 2 numbers to represent this data, right? So because it is on the floor, there is nothing on the z-axis. So now which means that I can compress this data by storing only 2 numbers, and now I can reliably reconstruct it. Now, of course, because you've all gone through linear algebra course, now the mathematical way to say this is that what is this floor? The floor is a subspace, right? So in the 3-dimensional ambient space, the floor is a subspace. And this floor contains all the essential information about this data. What you lose is not too much, right? So if you want to represent the floor, then how do you represent the floor? You have to represent the subspace. You represent the subspace using the basis vectors for that subspace, which means that if I can just understand what the basis vectors for these subspaces are, and within the subspace, how can I represent a point, which means it's just a linear combination of these basis vectors. So every point is just the combination for each of these basis vectors. And if in a big d-dimensional space, if you only have a k-dimensional subspace, you only store k numbers, right? So, and now, of course, if your data is all over the place, you cannot just store smaller set of numbers so that you can completely reconstruct the data. But you can still ask the question, what are those k numbers I need to store such that my reconstruction is as reliable as possible? And that's precisely what PCA is answering, right? So that is the intuition for what PCA is exactly trying to do. It's basically trying to find, it is essentially a compression algorithm. It's a lossy compression algorithm. You can think of it, that's how I would like to think of PCA itself. Let me give one more example. Maybe that will help you understand it better. Let's say we have the height and weight as the axis. Let's say the x-axis is height and the y-axis is weight. And I collect the data of all the people in this room, maybe 100 other people, and I plot them. Of course, you are going to expect a linear relationship. The taller the person, the heavier the person on average. So you are going to expect a linear relationship. So your points are all going to lie along the y equals x line, right? So now let's say I'm traveling along the y equals to x line, right? So each point from the origin is at a certain distance along the y equals to x line, right? So now let's say I have only that information, which means that I am representing each point not which perhaps may not be on the y equals to x line, but then I'm pretending as if it is lying on the y equal to x line. Now I look at what I lose, right? So for some points, I will lose a bit above the y equals to x line. For some point, I lose a bit below the y equals to x line, right? So, so that is basically noisy information. I'm not going to really gain anything there, right? So instead of storing height and weight separately, what I'm going to store now is one single number, which will be height plus weight, right? So if the height, if my data is of the form y equals to x along the line y equals to x, then height plus height plus weight gives me all the information about a data point. I don't need two numbers. Height plus weight is enough. Now, if I want to really calculate the noise also, I will also store height minus weight, right? So if height and weight are equal, height minus, for every data point, height minus weight is going to be 0. But some points, this height minus weight can be a small positive value. For some points, it might be a small negative value. I can actually choose to ignore that, right? So that's not really giving any structural information. That's basically noise. So instead of storing it as height and weight, I'll first reconstruct it as height plus weight and height minus weight. And now I'll realize that, well, if I reconstruct it like this, height minus weight is actually useless. So I can throw away height minus weight. So only thing that I'll retain is height plus weight, right? So, and that single number is good enough for me to reconstruct it as faithfully as possible. Now, if all the data points lie along y equals to x line, then height plus weight is the best number to store. On the other hand, if all the points lied along the line y equals 2x, maybe, then something else, maybe height plus 2 times weight might be the best number to store, right? So basically, we are essentially storing only some combination of these features, and remaining combinations don't really matter, right? So they are almost going to be 0. We can safely ignore them. So essentially, this is what I would say PCA is. Of course, the detail is you take the covariance matrix, take the eigenvectors, all that is detailed, but then essentially what you're doing is compression. Does that help, or maybe you already know these things? I'm just repeating. I think
it really did help a lot. It did. Just one question, like what you're trying to say, if I have someone who has a height, let's say 10, and a weight which is 50, just give an example, and I have another person, the height plus weight is going to be 60 in this case, right? And I have someone else whose height is 15 and his weight is 45. So the sum is again going to be 60. So in that particular situation, if I were to just store 60, then I'll have to
No. Okay, so here, okay, I understand what you say. So it's not always height plus weight, right? So if you have height as 10 and weight as 50, then if your height is 20, your weight, you should expect it as to be 100, right? So because there is a 1 into 5 times, right? So the weight is 5 times the height relationship, right? So which means that what you would store is not height plus weight. You might store 5 times height plus weight, which in this case would be 5 into 10 plus 50, it should be 100, right? So something like that is what you would store. So what is this? So maybe height plus 5. So basically, the coefficients that you're multiplying in the case where height and weight were equal, right? So hypothetically, let's say in some units they're equal, then you are just adding them, right? So adding height plus weight is just another way of thinking about this. You have a vector of height and weight, and then you are taking a dot product with the vector 1, 1, right? So which means that the direction 1, 1 is the most important direction, because if you project everything along this direction, which means that if you combine the features using these weights, then that has the most important information. That has all the information, right? So which line is it, right? So that line is what you want to store. And how do you store a line, right? So a line is just a span of a single vector, right? So, and that is the vector that will come out as the principal component if you do an eigenanalysis as well, right? So does that make sense?
Yeah.
Sure. Anything else? I think Rohit was the one who asked this question. Does this help, Rohit, or is there any other? Or maybe not. Maybe you are the one who asked it, right? So
yeah.
Rohit asked about the duality. Okay. Okay. So any other question.
Sir, regarding the PCA, so how is this connect? How can we connect this to regression, like the curve fit, which we have learned in a separate thing?
That's a very good question. So the difference is subtle, right? First of all, regression is a supervised problem, right? So you have data X, and then there is one label Y, and then you are trying to do some kind of a linear combination of the X's to predict Y. Now, even let's take the two-dimensional case, right? So now one might argue, right? So a natural question that comes is, let's say I have height and weight data, right? So let's say I'm given height and I'm asked to predict weight, right? So that might be my question. Now I can do it as a regression problem, or I'm now going to pretend that, okay, I'm not going to think of this as a regression problem. I will think of this as a two-dimensional data, and I will treat this as an unsupervised problem. And let's say I try to do PC, right? So you might just think of this as, forget the label feature part. I'll think of height and weight as two numbers. Each number is a point in a two-dimensional space. Maybe I'll do a PCA, right? So maybe that will also give me y equal to x line. We also saw in the regression also you're going to get something y equals to x line. So what's the difference, right? So that's a very natural, very important question that comes up. The difference is there's multiple differences. The most important difference is that what is the notion of error, right? So okay, so unfortunately I don't have a tablet today, right? So is there any way I can draw something somewhere and show? Is there
I think you can open a whiteboard, I think.
That's what I'm trying to see if I have. Okay, let me actually do this. Just give me a second. I'm trying to. Okay, the problem is kind of traveling and did not forgot to bring my tablet, right? So I realized it only this morning. But okay, so that's fine. Let me share my screen and tell me if you can see it. Can you see my screen?
Yeah, it's visible.
It's visible, right? Okay, so let's say. So we have x-axis, y-axis, okay, and let's say we have some points. Okay, maybe I'll take a few points. Okay, so let's say the x-axis is height, the y-axis is weight. Now, let us say we get this is the line that PCA gives us. So what does PCA tell us? So PCA tells us that there are two numbers that you need to save for each data point, right? So one is the height plus weight. How did I get height? Okay, maybe let's think of this as, for the purpose of exposition, let's say all this point passes through the origin. Okay, so how did I get height plus weight? It's height plus weight because I'll take height and weight as two numbers, and then I'll project it onto this line, right? So this is the y equals to x line, height equals weight line, which means that this is a span of the vector 1, 1, right? So 1.1, 1 is somewhere here, and then this is just the span, right? So which means that I'm projecting it onto the span of 1, 1. So that is what essentially saying that projection essentially means I'm just saving height plus weight, right? So which means what do I not save, right? So so let's take one particular point and see what do I lose because of saving this. So if I had to save one more number, what number would I save? I should save height minus weight. Why is that? Because this is the other direction, right? So once you have projected all your data along the direction of height plus weight, along the direction of 1, 1, what remains is just this, right? So for example, let's take one data point. Let me move this data point a bit so that it becomes easy. For this particular data point, what remains is this, right? So this point can be written as the sum of 2 points, sum of 2 vectors. One, right? So this is the vector, right? So this point, what do you mean by this point? This point is this vector, right? So this, let me give it a different color. The red vector can now be written as the sum of 2 vectors. One vector is the vector along the line x equal to y. The other vector is perpendicular, right? So which is along this line, right? So this is x equal to minus 1, right? So that is this line. So these are perpendicular to each other. These lines are perpendicular to each other. Now, what is PCA saying? PCA is saying that, well, you can find any 2 perpendicular lines such that if you project it along the first line, you retain as much information as possible. In other words, what you lose for each of the data points is very small, right? So you're losing for each data point this bit, right? So the bit that you lose is perpendicular to this point. So far, okay? This is what you're losing, right? So basically, I'm kind of, what PCA is trying to do is I'm trying to sum up these bits, right? So the length of each of these bits that I'm losing, and then I'm asking which direction should I project it on? Maybe it's this line, maybe here is another line, right? So maybe here is another line on which also I can project, but then I will lose more, right? So this would become a bigger, this point would lose more if I project it along this direction, right? And so on, right? So I'll then the sum of what I bits that I lose is more along this direction, this the one that I'm showing you now. Maybe I'll share. Okay. Problem is showing this is yeah. So let's say so I can either choose the yellow line or this thick blue line. But if I choose the yellow line, I lose more, right? So the bits that I lose are more. So I would rather choose the blue line, right? So the blue line corresponds to maintaining height plus weight. The yellow line corresponds to maintaining maybe height plus 2 into or 2 into height plus weight, right? So that is what I lose, right? So now what does PCA say? PCA say that find that line where you lose the least, right? So basically this bit I lose as small as possible. Now equivalently, now think of this geometrically, right? So if I want to lose in this direction as less as possible, now Pythagoras theorem, what does Pythagoras theorem say, right? So this point's length, this red vector's length is this blue vector's length plus this small bit, this length, right? So if I want to minimize the small bit, this bit, which means that I have to maximize this bit, right? So I have to maximize how much I retain along the direction in which I'm going to choose. Now that value is nothing but the variance of this data set along this direction. So that's why you can think of PCA as either minimizing error or maximizing variance, right? So both of these are exactly the same, because error plus this variance is just Pythagoras theorem right in front of you, right? So this is 90 degrees. So this square plus this square is this. So either you minimize the error square or you minimize this whatever remains here square, right? So now when you average that over all data points, that's just your variance of your data set along this direction. So you want to pick that direction that maximizes the variance. So that's the equivalent interpretation. Now coming to Shreya's question. So now let's forget this bit, right? So let's say we have found out that this is the direction in which most of the variance is, or least the error is minimum. Now, how is it different from finding the line that you would get from regression? Well, the crucial difference is that how you measure error. In PCA, you are measuring error as these bits. In regression, you are measuring error as how much is this, right? So for this X, you are predicting this as your Y, but then your actual Y is here. You should think of this as X and Y in regression, right? So you're predicting W transpose X as your answer, but then the actual is Y. So this difference, the square of this part, okay, let me make this in a different color. green, let's say. The square of the green part, if you try to minimize, that is what your regression is doing. Whereas PCA is doing, looking at a different thing, right? So that is, even if you want to think of your data set as an unsupervised thing and then try to run PCA, you're still not going to get the same answer as what you get as a regression, right? So that is that's something to think about, and it's not a good idea to do that because simply because then what you do with that, right? So how do you predict? It's not at all clear, right? So because once you combine these features, you finally want to solve a different problem in supervised learning, right? So given X, you want to predict Y, right? So how much is my prediction different from the actual is what you care about in regression, which is this bit. Whereas in PCA, there is no given an X, predict Y. You are only given X, and then you want to find that subspace where if you project, you lose less, which means that you care about this orthogonal projections, right? So does that clarify, Shreya?
Yes, sir. Yeah, it's very clear. Thank you.
Sir, can you repeat that maximizing variance part? Pythagoras.
Okay, yeah. So I'll repeat that. Okay, so for that, let's take a slightly different example, right? So same example, slightly different line. Let's say I give you two lines, right? So two candidate lines, where you can store the information, right? So where you can pretend your data is actually. What do I mean by that? Let's say, let me color this differently. Let's say you have the same data set. Now I want to. I have two candidate solutions, either the blue line or the green line. Which is a better fit in the PCA sense for this data set is what we are asking. Which means we want to see which one minimizes the error, right? So that's what we would say. So which means that okay. So maybe okay. I mean, if I really have to get this as the answer, I should make this maybe more closer to each other. Yeah. So let's say this is our data set. Here is one more. Right. So I'm just so now if I choose green line as my actual answer, then I'm losing these bits, right? So the horizontal bits are what I'm losing. So I mean, I might not draw it exactly horizontally, but assume that they are actually horizontal. Right? So that's because PowerPoint makes some. Okay. And so on, right? So I think this is good. So now here's the deal, right? So this is the data set. Now I'm projecting everything onto the green direction. Of course, it's clear that the bits that I lose along the blue line is much smaller than the bits that I lose along the green line, right? So these are longer. That's clear. So the error is larger if I project it along the green line. Now, where is the variance coming into picture, right? So now what am I saying when I project it along this line, right? So it means that I'm going to pretend that these points are actually along this line, right? So this point is actually this point. This point is actually this point, right? So here, right? So and so on, right? So there's one more very close to it. Right. So on the other hand, if I project it along the blue line, so of course these become. I'm pretending this point is this point, and so on. You get the drift, right? So I don't have to plot everything. I'll just plot 4, right? So now, as you can see, if you look at the green projection, they are crowded. When they are crowded, the variance is going to be low. Right, so they don't vary so much, right? So which means that if they don't vary so much, then you cannot distinguish them, right? So if they vary a lot, then it means that you can distinguish them still, right? So which means that the information that you want about this point can be thought of as the direction in which you have to project, so that the points are the variance is as high as possible, right? So which means that if you think of this data set as, if I pretend this data set as these points, I still have some variance in this direction, whereas in this direction it's very bad. Now, what is the worst direction where you can project? Let me ask you that question. For this data set, which do you think is the worst direction where the variance will be as small as possible?
Maybe x-axis, or maybe opposite of the gradient. Yeah.
The x-axis. Okay. Why do you say that?
No, I just trying to guess. Sorry, I think.
Sure, please. Yeah, but I'm just trying to understand what is your thought process.
Yes, I think x-axis, because some of the points are overlapping. When it comes to, so in that case, we'll not be able to distinguish, and the variance is basically the mean minus the points, right? So if the points are very close to each other and they are okay, now they're not overlapping, but some of them were overlapping before.
No, that was, I mean, I pretended those points were on this line, right? So they were actually not on this line.
Okay, right. Okay.
Yeah. So
will it be the line perpendicular to the blue line?
Perfect. It has to be the line perpendicular to the blue line, right? So let's see why. Right, so now this point, this point is going to go here. This point is going to, I mean, you may or may not visually see it that well here, but then see all these points are going to kind of get get crammed together, right? So they're going to be very, very close to each other. Do you see what I'm trying to say here? So this point goes here, right. This point goes here, and so on, right?
Yeah, basically they're squished. Yeah, I get that. Thanks, Shreya. Yeah.
They get too squished, right? So which means what? That's the direction where there is no information. All points look similar in that direction. If I pretend that this point is actually in this direction, then I don't distinguish between the points at all. If all points look similar in a direction, I don't need to store information about that direction. I can throw away that information out, which is precisely what we are doing, right? So in PCA, what we are saying is that here is the direction where most of the information is, and here is the direction where the least information is. I'll store only the direction where the most information is, and the orthogonal direction, I'll throw it away, right? So that's precisely what PCA is doing, right? So your first principal component, at least in 2 dimension, your first principal component will give you the direction of the highest variance. The second principal component is going to give you the direction of least variance. But in higher dimension, perhaps the second principal component may also have some information to distinguish the data points, right? So you cannot just throw away everything other than the first direction. You may want to store some k directions, and then the remaining doesn't really matter. You can throw away the remaining d minus k directions, right? But the important point is that these are all now orthogonal to each other, right? So, and that's precisely your eigenbasis of the covariance matrix, right? So that's again mathematics, but that's how you do PC. But the point is that you want to find the directions where the most information is. If the most information is in one direction, then the perpendicular direction will have the least information in 2 dimensions. So you can choose to store only one direction and throw that away, right?
Yeah, and definitely. So it helps in to visualize this in 2D, because the eigenvectors are going to be orthogonal. So obviously it is clear, right? That thanks for pointing that out. You should have been able to guess it. So that way, if you're able to take it in one eigenvector, then the other eigenvector is practically meaningless.
Sorry, practically
meaningless. Yeah.
Okay. So let me ask you a question. Where do you think both the eigendirections? Give me a data set where both the eigendirections are going to be important.
When probably the points are too clustered.
Sir,
no, the points are too far apart.
Yeah, you are getting the intuition, right?
Yeah.
So basically, you somehow want to say that, well, I need information in both the directions, right? So to represent the point, I don't just need information in one direction. So when can I say that information in one direction is enough? Well, if the points are all kind of clustered around one line, right? If that does not happen, let's say you take the circle and then put points uniformly at random everywhere in the circle, right? So now every direction is an important direction, because if I project it on any direction, I'm going to lose some significant amount of information in the orthogonal direction, right? So because there is no line in 2 dimensions, you can think of there is no line which kind of represents this and most of the information. In this particular example, there is a line, right? So and that's why we can choose to throw away the orthogonal project, the second eigendirection. That's no longer useful. On the other hand, if it might be the case, right? So maybe I'll show you if it helps. Maybe I'll show you. I mean, it should be easy to construct a data set. Of course, we are not doing numbers at all here, so you have to kind of take my word as gospel, but you can go ahead and try these things, these examples. Let's say I just put points randomly along both the directions, right? Oops. Everywhere around, right? So of course you need to make sure, well, PCA would need mean to be 0 to find these directions, but let's assume along the circle. Let's say they are just, okay, I don't know if this is going to be a question in your final exam, but anyway, so let's say it is just spread around the circle, right? So now, okay, so here is the question. So this is spread along exactly along the circle, let's say. Assume I'm drawing it on the radius of a circle, 100 points. Now, what is the first principal component? Which is the first principal direction for this data set? What would be your guess?
We could just take the 2 axes, right? They could be the.
Which axis? I mean, I'm just asking for the first principal component.
You can take any of the 1 axis, right? Either, I mean, actually there are 4, positive, negative, x and y.
Actually only 2, right? So I mean so you only look at the span, right? So it's a subspace that you need to look at. It's either the x-axis or the y-axis is one direction. Yes. Well, those are fine. I agree, both are okay. Now, there is nothing wrong about this direction. How is this direction any less than the x-axis or the y-axis?
Yes, sir. The entire radian space, because it's a circle point, right? So that way,
yeah,
there is a equal probability of finding 2 points in any direction.
Correct. In fact, you will see that every direction is an eigendirection, right? So if you actually look at the covariance matrix, right? So now let's try to actually do the calculation for the covariance matrix. So I mean, if I randomly put these points, right? So let's say the x-axis is chosen independently of the y-axis. If there is no relation between the x-axis and the y-axis, I choose 10,000 data points like that and give you the data set. Now, how do you think is the covariance matrix of that data set going to look like? So here is what I'm doing. So I'm generating x-axis uniformly at random, let's say from 0 to 1, y-axis uniformly at random from 0 to 1, independent of the x-axis that I choose. And now here's 2-dimensional points, 10,000 such points. What would you do? You would do your PCA would take the covariance matrix, take the eigenvector. That's the step, right? So now my question is, how do you think is the covariance matrix going to look like?
We'll have very large values.
So what is the, let's first ask, what is the dimension of the covariance matrix? So these are 10,000 points in R2, where each coordinate is independent of each other. So in what dimension is the covariance matrix going to be?
It's still R2, right?
It's a matrix though, right?
Yeah, it's a 2 by 2.
Good. It's a 2 by 2 matrix because you only have 2 features. Yeah. So it's going to be a 2 by 2 matrix. Now my question is, how do you think is this matrix going to look like? What's your guess?
I think it's going to be 0.5, 0.5 each.
In all the 4 values? That's your guess? Why?
Because they are equally distributed on both the sides, right? So 0 to 1, it can be absolutely randomly, we are saying, but there must be some logic to that. And uniformly, if we take any points, then I think the difference in the covariance is nothing but the matrix that it's kind of variance only. It's a variance of X into variance of Y. That's what I understand from what you're trying to say. And if variance, it's going to be 0.25 in that case, then 0.5 into 0.5, that is 0.25.
Okay, I'll come back to you. Any other answers or guesses? So here's the way to understand covariance matrix, right? So the diagonal entries of the covariance matrix are just going to be the variance along each direction, right? So you have 2-dimensional data. So your covariance matrix 1, 1 entry is just going to be, I forget the Y dimension. I just look at the X coordinate and then ask what is the variance of this set of data points, right? So if you think of these as 1-dimensional data points, that's your diagonal 1, 1 entry. The 2, 2 entry is just going to be the variance of the Y coordinate, right? So that's it. The interesting things happen in the off-diagonal entries in a covariance matrix. Now, what is the 1, 2 entry is going to tell you? Well, it's going to tell you how much information, within quotes information, is the value of the X coordinate giving you about the value of Y coordinate. In other words, if X increases, does Y also tend to increase on an average? If it does, then that value is going to be positive. If X increases, if Y tends to decrease, if they are inversely proportional to each other, then that value is going to be negative on an average, right? On the other hand, if I give you X, you cannot say anything about Y, right? So if X and Y are completely independent of each other, then that value is actually going to be 0, right? So these are completely independent values, right? So that's what it basically tries to say. Now tell me what is going to be the covariance matrix of the data set that I described earlier.
It's going to be an identity matrix, I think.
Yeah, so it's going to be a diagonal matrix, right? So the variance could be some number, but you're right? So the main point is that it's going to be a diagonal matrix, right? So now let's say it's an identity matrix. Now, what are the eigenvectors of an identity matrix?
Identical.
Mm-hmm.
They are same.
Same with respect to what?
With respect to diagonal entries.
So Ix equals lambda x. Which vector satisfies?
It's all vectors in R2.
Yes.
Every vector in R2 satisfies this, right? So identity times x is x. With every vector has eigenvalue 1. So every vector is an eigenvector. The geometric picture is every direction is equally same for that data set. It does not matter which direction you project onto it, you get the same amount of information. Every direction is equally important. But if your covariance matrix is not a diagonal matrix, then we are in business. Then it means that there are some directions which are more important than other directions. Now, what PCA is telling you is that, well, I'm going to find you those directions. And those directions are the eigendirections of the covariance matrix, right? So now the eigenvalue tells you how important is that direction. In the case of identity matrix, covariance matrix, all eigenvalues are the same. Lambda is going to be 1. Ix equal to lambda x, lambda is going to be 1, right? Whereas if your covariance matrix is something else, then some eigenvalues are going to be larger, some are going to be smaller, right? So the larger ones have the more information, the smaller ones have the lesser information, right? So that's one way of thinking about PCA also. Now, the other interesting thing, what would happen is that, so now let's go back to this example, height and weight. And now I've realized that, well, I take the covariance matrix. Now, what is going to be the off-diagonal entry? It's still going to be a 2 cross 2 matrix. Now, what kind of a value should you expect in the off-diagonal entry for this covariance matrix, for this data set?
A positive number.
Why?
Because there is some correlation, reasonable correlation between height and weight. So actually a reasonably large, less than 1, but it will be less than 1, but as close to 1 as possible, right? So the closer to 1. It's going to be closer to 1 than closer to 0. Let me put it that way.
Precisely. Right. So in general, you are expecting weight to increase as you increase height. So there is a positive correlation between height and weight. So your off-diagonal entry is going to be positive. Right. So somehow you do the eigenanalysis and you figure out that, well, height plus weight is the direction where the largest eigenvalue is, which means it's the most important direction. Height minus weight happens to be the least important direction. Now, if I, instead of storing the data as height and weight, if I instead represent the data now as by using two numbers, which are height plus weight and height minus weight, right? So now let's think of this data itself as, well, every data point I'm going to, instead of storing height and weight, I will store as height plus weight as one number and height minus weight as another number. Now for that data set, if I compute the covariance matrix, how do you think the off-diagonal entry would be? Is the question clear? Initially, I had height and weight. I give you the data set. What you do is, for every data point, instead of height and weight, you store two other numbers. You throw away this data set. Instead, you store you create a different data set with height plus weight and height minus weight as the two numbers. Now, this is a new data set. I can construct the covariance matrix of this data set also. My question is, what do you think will be the off-diagonal entry of this data set?
I was trying to say 0 or going to be minus 1, close to minus 1. I think 0, closer to 0.
Why?
Trying to guess that the correlation is very, very low between these two values.
Because they are perpendicular, right? So they're perpendicular in a ways. It's absolutely, there is zero correlation. And
is it?
Yeah, go ahead.
Are they perfectly correlated? Sorry.
Why do you say that, Shreya? What do you mean perfectly correlated?
Because if I take any 2 points, the relationship will be sort of, there'll be some sort of relationship between them, right? It'll either be proportional or.
Let's ask the question. Let's say this data set, if I tell you the height, right, for a new data point, right? So let's say you've seen this data set. If I tell you the height for a new data point, which is 100, what would be your guess for the weight?
100.
100, right? So that's the reasonable guess that you're doing. Now, let's say for the new data set, I'm telling you the height plus weight is 500. What would be your guess for height minus weight?
0.
Okay. So if I tell you the height plus weight is 50, what could be your guess for height minus weight?
Again 0.
Right. So which means independent of what height plus weight is, your height minus weight is always, you're trying to guess it as 0. Right. So in some sense, height plus weight is not really giving you any information about height minus weight. Right. So by knowing height plus weight, I don't gain any new information about height minus weight. Which means in this, if I think of my axis as height plus weight and height minus weight, these two axes are actually independent of each other, or rather uncorrelated to each other. I should not say independent. That's not the right word. They're uncorrelated from each other, right? So, which means you can also think of PCA as finding those directions which are uncorrelated from each other. Initially, the data set had correlated features. Now I'm trying to get a new set of features which are completely uncorrelated from each other, which means that I can then only retain the most important uncorrelated features and then throw away the rest. That's one other way of thinking about PCA also, right? So PCA is it's actually doing decorrelation of features, right? So that's also an interpretation of PCA. Does that make sense?
Yes. We are basically trying to find the most important directions on which we can represent the data in a lesser space. That is PCA.
it's also all the other things that we have discussed, right? So the way, I mean, it's a very beautiful idea, right? So it's not at all a priori clear why the eigenvectors of the covariance matrix have to do anything to do with the interesting directions of the data and so on, but it's beautiful, right? So finally, end of the day, it's Pythagoras theorem, and that's all it is, right? So once you know you're going to maximize variance, then the higher dimensional analog is the covariance matrix, eigenvectors of the covariance matrix.
Right.
Okay. Yeah. Any other questions about PCA?
So I wanted to ask, like, how do then PCA relate to optimization? Because it is probably going to converge faster in the sense that the optimization problem would be an easier problem to solve if we do PCA.
Which optimization problem would be easier to solve?
Say we have a constraint optimization problem. So in that case, from what I'm trying to understand, because I'm going for a dimensionality reduction, right? So in that case, in any way, is it going to reduce the size of my optimization problem?
Exactly. Right. So you should think of PCA as a pre-processing step. Right. So you have a lot of data, but you have a hunch that, well, not all dimensions are important. There are some correlations among these features. I do PCA, I pick the top few, maybe top 100 directions. I retain only those, which means that instead of 1 lakh numbers, I'm only storing 100 numbers. Now your optimization problems, typically the complexity of the optimization problems are going to be directly related to the dimensionality of the data itself, right? Now, because we have reduced the dimension a lot by doing this pre-processing step, your optimization problems are also going to, optimization routines are also going to run faster, right? So that's the next step, right? So yeah, in that sense, yes. But the motivation is not so much that you need to make the optimization step faster. That's like a happy consequence of this. But the motivation is more to retain only the most important parts of the data. You don't want to retain the noise, right? So that's why you do this dimensional regression.
Yeah, I understood that part. I was just trying to find the correlation with optimization as well.
Yeah, it does help in optimization, right? Yeah. Anything else?
So suppose I want a plane instead of line, then should I take the first two?
Yeah, you know the answer. That's the answer, right? So if you want a plane, you take the first two. Then the subspace spanned by those two directions will be the plane, right? So that's the example that I started off with, right? So you have the data in 3 dimensions, 3 numbers, but then all of them are distributed on the floor, which means you can just take the plane spanned by the floor, right? So yeah, that's precisely what.
So sir, I just want to get my idea right. I'm just thinking of it in the machine learning perspective. If I were to predict the age of a person using height and weight, only these 2 parameters. My y is age in this particular case, and there seems to be some correlation, like you just mentioned, height and weight is kind of correlated in general with most people in average. So in that case, I'll be just considering one line for my pre-processing step, and then I'll be running all the algorithms, whether that be linear or whatever algorithms I end up being. That is what I'll be doing. Is this idea right?
Correct. You're right.
Okay.
Yeah. So you will have a lot of downstream questions, right? So I mean, I don't know how much of machine learning problems you've been exposed to, maybe not in this course, and definitely you would have seen other places as well. So the downstream problem might be a classification problem, right? So now, a good idea is to do PCA and then do a dimensional reduction and then ask the question, well, if I do the classification, does it make it any better, right? So now, with an abundant caution that PCA is unsupervised. The downstream problem is a supervised learning problem, right? So you may want to, it might backfire in the sense that you might reduce your dimension, thinking that in the sense of projecting onto the best subspace and leaving out the other bits as noise, you might throw away the noise in an unsupervised way, but it might so happen that all the action is in the noise for your downstream problem, right? if that is the case, then doing a PCA might actually backfire, right? So it might reduce your accuracy by a large amount. For example, in the same problem, if it completely I'm going to later predict something on a data set. If I am totally unaware of that prediction y, let's say it's a binary classification problem, which means the prediction is positive or negative, right? And now if it so happens that for this data point, if I'm going to predict it as positive or negative, only depending on this bit, right? So this piece of here, whether this is maybe whether this is on this side, or whether it is on the second quadrant or the fourth quadrant, right? So it can be either in the second quadrant or the fourth quadrant. That's the only possibility for this piece. So if I'm going to use this piece as critical for my classification problem, if it so happens my data set uses this piece critically, but now if I do PCA, I lose this piece, right? So there is no way to reconstruct this piece because I only maintain height plus weight. But then if height minus weight is what determines my final output, classification output, then I'm screwed, right? So because I don't have any information about height minus weight, because I'm only retaining height plus weight, right? So now that's a bad idea of doing PCA in that case, right? So you have to be slightly careful, right? So it's not like it's a compulsory step always before you do your classification, but it's very rare that the noise is going to contain some important information for your classification, but it could, right? So that's why I'm saying you have to be careful about doing PCA.
So I was working on one example. Maybe you can just correct me if I'm wrong. So what we were doing is that so we have typically cars which are being manufactured on shop floors. And so there are a lot of robots which does thousands of welding events in one single day, right? So what they were trying to find out that, if there is any spike in, say, a pressure, or another was voltage, I think. So they were trying to find out those specific records because they would mean that something is wrong in the system, right? So basically they're trying to find out the kind of noise in the system, and they wanted to act on those records. So those were the events which led to the failure of that welding machine, say, for example. So in this case also, I guess PCA would not be the right approach, because we are basically trying to find out the noise which is of importance to us, right?
Yeah, you're absolutely right. So so there are methods which does something like PCA, but then it's a supervised method, right? So it's called Fisher's linear discriminant analysis. Let's not get into that in this discussion, but just to tell you that precisely for this problem, there are other methods that people have developed, which is where you take into the account the supervised label that you want to predict, and then find directions which are most important for making this prediction. And such methods are called, one such method is called Fisher's linear discriminant analysis, but next semester.
Yeah.
Thanks. Sure.
Sir, is there any characteristics, any way we can identify, okay, this is the data set we should do PCA? Like you just mentioned, is there something of that?
Yeah, so the good thing to do is, again, you learn this, learn something called as model selection later. So basically you do PCA and try to do a prediction on some held out test data, which is called as a validation data. If your PCA is not at all helping on your validation set, then perhaps the action is in the noise, right? So you should not be doing this. That's the standard way to do it. Good. Any other clarifications about PCA? And I hope this made it slightly better than what you had understanding before. But yeah, if there are any questions, let me know. Okay, so maybe I'll stop sharing this. Okay, so I think the other question was about duality and why we care. So at least from a machine learning point of view, one of the very crucial algorithms called the support vector machine algorithm, about which also I described a bit. I mean, I did not really describe the algorithm or anything, but I did put down the form of the optimization problem in the algorithm. I don't think that helped so much if you have not seen the support vector machine before, but that algorithm crucially uses the notion of duality. Right, so duality is kind of telling you that you, instead of solving one problem, can I solve a different problem and arrive at the same result? Right, so that's the high level spirit, right? So of the question, and the way that we developed this dual problem is kind of saying that. The main reason why, let me tell you why it's useful, right? So in the machine learning context, maybe that will motivate a little bit. The reason why it's actually useful is in practical cases is because you may have a problem in very, very high dimension, but you may have a very less number of data points, right? So now typically, your data points are in, let's say, 1 lakh dimension, and you have 1,000 data points, let's say, right? So now you want to learn some kind of a linear combination of these features, right? So you have 1 lakh features. Now, which means that you are searching in a 1 lakh dimensional space for that best linear combination, for that best feature. Somehow you're set up an optimization problem, you're trying to search for the best feature. Now, this is a search in 1 lakh dimensions. Now, the dual problem, it's a constraint optimization, right? So, so it's a search in 1 lakh dimensional space with 1,000 constraints, where 1,000 is the number of data points. Each data point should either lie on one side of the line or other side of the line, as given by the labels. Let's say, let's forget it. Let's say there is some constraint, one constraint for each data point. So you have a 1 lakh dimensional problem with 1,000 constraints. Now the dual problem switches this, right? So now the dual problem is a 1,000 dimensional search with 1 lakh constraints, right? And these, in some cases, searching in a lower dimension might be much, much easier than searching in this 1 lakh dimensional space, for example, right? So if you want to run a simple projected gradient descent, let's say, running it in 1 lakh dimensional space means that you are computing a gradient of dimension 1 lakh at every step, and then moving towards the optimal, and then doing a projection. All those things are happening in every step. Whereas a projected gradient descent in a 1,000 dimensional space might be much, much easier, right? So even if you have like a lot of constraints. In this particular support vector machine example, dual problem becomes much, easier to solve. At least the constraints become much simpler for the dual problem. And so that's why we typically go to the dual problem. There is one other very, very important reason why one goes to the dual problem. And it might be very hard for me to explain it now because that means that I'm actually explaining the entire algorithm to you. But nevertheless, I'll try to give you a flavor of what this is. Maybe when this algorithm is being discussed next semester, you will kind of try to relate it to what I'm saying. It's a good practice in machine learning if you can write your optimization problem in a form that involves what is called as a gram matrix. A gram matrix is if you have n data points, a gram matrix is a n cross n matrix where the ijth entry is just the dot product between the ith data point and the jth data point. It kind of measures how similar the data points I and j are, right? So that's a gram. That's called a gram matrix. Now it's an n cross n matrix. Now the reason why this is very important is because now if you somehow manage to get your optimization problem into a form that only depends on the dot product between pairs of data points as opposed to the exact data points itself. Let's say somehow you get that, right? So maybe, which means that there might be two different data sets of entirely different points, but then their pairwise dot products are exactly the same, right? So then the gram matrix is going to be the same, right? So if you somehow don't care about the data points, but if your algorithm or optimization problem only cares about the similarity between data points, if you can express your optimization problem in such a way, and a lot of problems can actually be expressed in such a way, as we will see later on, then something very, very important can be done. You can move from linear models to non-linear models in a certain way, in a certain sense, which I won't describe now. It's called the kernel trick. But the idea is that if your algorithm can be written as an optimization problem which involves a gram matrix, then your algorithm can be, what is called as kernelized, which means that instead of learning a linear model, you can also learn a non-linear relationship between the data on the output, right? And that is very, very useful because in real world, seldom you are going to find data sets where the relation between y and x is linear. It's often non-linear, it's often going to be complicated. But now this is saying that if you understand the linear model really well, and if you can somehow manage to set up your optimization problem using this similarity, dot product similarity between pairs of data points, then going from linear to non-linear is just one step. It's like you don't, without any computational, spending too much on the computation, you can go from linear to non-linear models. Now, why am I describing this? Well, the support vector machine algorithm, which again you will see in much detail next semester, the primal problem does not have anything to do with the dot products between data points. On the other hand, if you write the dual problem, it turns out that the dual problem will only depend on the gram matrix. Well, it will depend on a few other terms which are okay, which are not too important, but the key thing is that the dual problem is going to depend on the gram matrix. Now that is like a treasure, right? So once you have done that, now you can say that I'm not going to simply learn only linear models, I can also learn non-linear models. I know a lot of things, there are details that are missing at this point, but I mean, if I fill in the details, then that means that I'm teaching you that algorithm, right? So I don't want to do that now in this discussion. All I want to say is that by just going to the dual of the support vector machine problem, you gain two things. One is that the dimension in which you are searching might reduce a lot depending on how many data points and constraints you have. That is one advantage. The second and the most important advantage is that you can express your optimization problem itself in using a gram matrix, which means that you can also learn nonlinear relationships between features and output. And that becomes very, very crucial for machine learning applications. I mean, that's the whole reason why these algorithms became so popular in the 90s, the support vector machines, and even in the early 2000s. Right? So it turns out now let's talk a bit about this gram matrix from just because we spoke about PCA. Let me also talk a bit about PCA, right? So let's say for example, you have your data set in 3 dimension, which is all on surface of a sphere. Let's say there is a sphere in 3 dimension, and all the data points are on the surface of the sphere, right? Now, we already saw, right? So we just saw that if you take the covariance matrix and try to find the eigenvectors of the covariance matrix, it's going to be all directions are going to be equally important, right? So because it's completely spread across the surface of the sphere. But we can see that there is some structure here that we are kind of missing out on, right? So just that the structure is not linear. if you insist to find linear subspaces, then your PCA will think that all directions are equally important, but you're missing the structure. Now you can ask, well, can I do a nonlinear version of PCA? Right? And for the nonlinear version of PCA, it turns out that you can actually do this if you write your PCA's optimization problem itself in terms of the gram matrix, which you can actually do. And that is actually called as kernel PCA, wherein it is as if you are moving from a lower dimension to a much more higher dimensional space, and then again taking a PCA in that higher dimensional space. And in that higher dimensional space, what would happen is that the linear relationships in the higher dimensional space would correspond to nonlinear relationships in the lower dimensional space, which means that the whole sphere would actually go to a subspace in a higher dimension, which means now if you're doing a PCA in this higher dimension, it would actually capture this sphere in terms of a linear subspace, right? So that's there again, there you will encounter these gram matrices. So they'll become very, very important. I don't know if kernel PCA is going to be covered in a later course, but you can look it up. So that is again based on this gram matrix, which is somebody that you will again and again encounter when you actually do machine learning applications. I know I've not given all details about these algorithms, but I hope at least I've convinced you in some sense that duality is an important notion for machine learning, right? So I hope I did that. But yeah, if there are other questions, I can take.
So this gram matrix sounds very similar to A transpose A. Is there any connection with the singular value decomposition?
Great. Wow. Good. So okay. So by A, let's say your A is your data matrix.
Yeah.
Now your covariance matrix is just A transpose. If you think of your A as your data matrix, right? So if your data is like D cross N, your A is a D cross N matrix, then your A transpose is going to be a D cross D matrix, which is a covariance matrix.
Yeah.
And the eigenvectors of the covariance matrix is what gives you PC. Now, what are we saying? We are saying that instead of A transpose, exactly as you mentioned, your A transpose A is simply the dot product matrix, right? So now what's the relation between this and A transpose? The interesting relationship between this is that for both these matrices, the eigenvalues are exactly the same.
Yeah.
And if you know the eigenvector of one of these matrices, you can get the eigenvector of the other matrix. You can reconstruct the eigenvector of the other matrix. So this is precisely what people do. So essentially, if you have, let's say, a face recognition application, right? So you have lots of faces. That's your data set. You have, let's say, 10,000 people's face in an organization, let's say. Now, but each face is represented as let's say a 128 cross 128 picture. But then each pixel is red RGB, right? So which means it's 3 numbers. Which means that if you want to vectorize a face into a vector, it's going to be 128 into 128 into 3. That's going to be a large thing, right? So that's going to be huge. So which means that your D is much, much larger than the number of data points that you have in this case. So if you want to do a PC, this is a different motivation for why you may want to do A transpose A as opposed to A transpose. That's what I'm trying to get at. If you want to do a PCA, you have to compute the eigenvectors of a D cross D matrix. And that would take order of DQ, right? So that's eigenvector computation is as good as like doing some kind of an inverse of a matrix. And you can do slightly faster, but let's say the naive or the basic algorithms will take order of DQ. And when D is much larger, the number of features is much, much larger than the number of data points. You can do PCA, but then you're going to take a lot of time. Now, the question is, well, can I do something in N cross N, right? So can I use a N cross N matrix? Can I do something and then still solve the PCA problem? If I ask that question, the answer turns out to be yes. And that's where you need to come to the gram matrix. From the covariance matrix, it's the other way of looking at the covariance matrix in some sense, right? So instead of a D cross D matrix, you now look at an N cross N matrix. Now you solve the eigen problem for the N cross N matrix. matrix. Now that is n cubed. Now if n is much smaller than d, you can still do it quicker, right? So if you have lesser number of data points than the features, this is a faster problem to solve. But then your goal is still to solve the eigenvectors of d cross d matrix, right? So that's what PCA is asking you. Now you have only got it for n cross again. So now it turns out by taking advantage of the fact that these are actually transposes of each other and their eigenvalues are the same, you can actually go from the eigenvectors of this to the eigenvectors of that in a fast way, right? So which means that now what you've done is that the motivation here I gave is that if you have a lot of dimensions, then you can go from you can, instead of doing a d cross d, you can do a n cross, right? So now think of a different problem where I don't have a lot of dimensions. My d is smaller. I have a lot of data points, n data points, but my dimension is smaller. But the problem is that the data points are not on a linear subspace. They are in that, let's say, a non-linear. They have some non-linear relationship. Now PCA is going to fail. I can solve the d cross d problem quickly, but my PCA is going to fail. So what I would actually do is I will force my dimension to be higher, right? So instead of, for example, a simple example is that let's say my features are height, weight, I don't know, body mass index, right? So let's say these are my features. Now these three have a relationship, but then they are not a linear relationship. I don't remember the formula, but your body mass index is like height square by weight or something. There is a non-linear relationship, quadratic relationship here. Your PCA is not going to find this relationship, right? So because PCA will only tell you that combination of sometimes some number into height plus some number into weight plus some number into body mass index, which is the most important. That's all PCA can find, and that's not going to be useful at all because the inherent relationship is quadratic. So now what you do is that you forcefully make your features as not just height, weight, body mass index. You will, given these three numbers, now I will force it as height, weight, height squared, weight squared, height into weight into body mass index. I'll make all the quadratic combinations. I'll pretend as if this is my new data set. Now this is a higher dimensional data set. Now your non-linear quadratic relationship in the lower dimension becomes a linear relationship there. Let's say height squared plus weight squared minus body mass index. If this is what is the relationship that you care about, now it's a quadratic relationship in the original dimension. But if you had height square as a dimension itself and weight squared as a dimension itself, then it's 1 times height squared plus 1 times weight squared minus 1 times body mass index. That's just a linear relationship, right? So now you are forcefully going from a low dimension to high dimension. Now, why only quadratic? You can go to any number of higher dimension. You can go to a cubic. You can go to a 4th power, any number. But then the penalty that you're paying is that the higher the dimension that you go, the more the features you're going to have. Because there are going to be multiple cross terms, right? So height into weight. Height, if you go to cubic 3rd dimension, then 3rd power, then you will have height into weight square, weight into height square. All these combinations are going to come. So the number of features that you have to maintain will go exponentially quickly to a very high dimension. Now, what you do is that, well, now this becomes a problem of d being higher than n, right? So you have pushed your small d to a large D, capital D. Now this is a large D, but then now you have a small n. But we already know how to solve the large D, small n problem. Instead of A transpose, you do A transpose. As somebody says, just like polynomial regression. Yeah, so that is the supervised analog of this. This is an unsupervised analog. Yeah, so now you forcefully go from low dimension to high dimension, and then take advantage of the fact that you don't really need to compute the d cross d matrix at all. You can work with the n cross n matrix and still solve the d cross d matrix's eigenvector problem, right? So, and that's why you can go to any high dimension, right? So if something interesting happens, if you can express your problem as in the form of a gram matrix. Right? So that's why if your problem is amenable to be expressed in the form of an n cross n matrix, a gram matrix, then all these tricks can happen. Right? So, and it turns out in a lot of cases it can happen, and that's what gives the computational power for a lot of these problems. Again, this is, I mean, to really do justice, I need to do the math, but I hope I just gave a high-level idea.
Got it, sir. Thank you.
Yeah. Okay. Any other questions?
So can you please give an intuition for eigenvalue and eigenvector also?
Okay. So let's look at it this way. What is the simplest matrix that you can think of?
Identity matrix.
Identity matrix. Very good. What is the next simplest matrix?
Diagonal matrix.
Diagonal matrix. Now, what if I told you most matrices are diagonal, just that they are hiding themselves from plain sight? So that's essentially your spectral theorem, right? So it's basically telling you what is a diagonal matrix. Well, if I give you a vector, it's going to scale each component by some value, right? So if I give you x1, x2, x3, you have a diagonal matrix with d1, d2, d3 as the diagonal entries. Then you're going to get d1, x1, d2, x2, d3, x3. This is what you're going to get as the output. Basically, it's scaling each component by some value. Now I'm saying every matrix or most matrices are doing only this. Just that the initial vector that you give, you cannot measure it in the standard basis. You cannot represent this vector in the standard basis, which means that you cannot measure x1 into 1, 0, 0 plus x2 into 0, 1, 0 plus x3 into 0, 0, 1. That's x1, x2, x3 measured in the standard basis. Don't measure it in the standard basis. If you measure it in an appropriate basis, right? So if I think of the same vector as expressed as c1 into some other u1 plus c2 into u2 plus c3 into u3, if I measure it in some other basis, then all that matrix is doing is only scaling in each dimension. It's a diagonal matrix. Now, which basis is that where a matrix acts as a diagonal matrix? That matrix is just your basis matrix. Those directions are given by your eigenvector directions, which means in those directions, all that is happening is scaling. Now, if you take an eigenvector direction, eigenvector itself as the input, right? So let's say your eigenbasis is u1, u2, u3, u4, the 4-dimensional, 4x4 matrix. u1, u2, u3, u4 are those 4 vectors. Now I'm saying that in this, if you represent every vector in this basis, then what the matrix is doing is just it's a diagonal matrix. Now, what does that mean? Now, what is the representation of the vector u1 in the basis u1, u2, u3, u4? What is that? Let's say I give you the basis. The basis is u1, u2, u3, u4. You understand what is a basis and all that, right? So the basis is u1, u2, u3, u4. It's an orthonormal basis, let's say. Now I ask you, how will you represent the vector u1 itself in this basis? How does that representation look like? What would that be?
1, 0, 0, 0, like
1, 0, 0, 0, 0. Right? So it's just, so u1 in this world is just 1, 0, 0, 0. Right? So which means that if I multiply a diagonal matrix with 1, 0, 0, 0, it is just going to become lambda 1, 0, 0, 0. So now what is lambda 1, 0, 0, 0? Now if I again go back to the original basis, right? So u1, u2, u3, u4, that is just lambda 1 times u1.
Yes.
Right? So essentially what we are saying is that if you represent your matrix in the correct basis, then most matrices are just diagonal matrices. Most interesting matrices for machine learning are just diagonal matrices. We are just looking at it in the wrong way. Right? So for example, all symmetric matrices, real symmetric matrices are diagonal matrices. You should think of them as just diagonal matrices. Just that if you represent it in the right basis, they become diagonal. Which is the right basis? It's the eigenbasis. Right? So because diagonal matrix is just scaling in each direction, which means then if you rework what should be the property of the basis, then these should be a set of vectors such that the matrix should just scale that vectors, which is our definition of eigenvectors. Right? So that's one way to understand. your eigenvectors. Eigen, by the way, I think in German means characteristic, right? So it just says that this is what characterizes the matrix as an operator, right? So what all the action in the matrix is just in these directions. If you understand the matrix in these directions, you understand the matrix everywhere, right? So in these directions, it's not doing anything complicated; it's just doing scale. So which if you take a different basis, it might not do scaling. It might also do some rotation and so on, right? So that becomes complicated. Right? So these are not simple atomic operations, right? So but then scaling is a very, very simple operation. So if you understand that basis where each component is just being scaled, so then that's the simplest way to understand a matrix, right? So that's the eigenvectors.
So it's not wrong to say that eigenvectors are nothing but scaled bases. That's what it is in a lot of ways.
So eigenvectors are, well, formal definition is eigenvectors are those vectors where the matrix as an operator does nothing but just scale.
Right.
Now, if you collect all such vectors, now that if you look at that as a basis, okay, I always have a caveat that it's not always, whatever I'm saying is not true for all matrices. For all nice matrices, let's talk about nice matrices, right? So if you collect all the eigenvectors and think of that as a basis, now what is a basis, right? So it's like, think of it as your x-axis and y-axis. Think of these as roads, right? So you have a road in this direction or in this direction, right? So which means to go to any point, you have to go in this x-axis direction and then go. But then if your roads are in 1, 1 direction and 1, -1 directions, then you can reach any same point using these roads as well, right? So which are those roads, right? So where if you now represent each data point as the amount of distance that you want to travel in each of these roads, if that is how you're going to represent a data point, right? So of course, if the point 5, 4, you represent it as 5 units along the road, x-axis road, 4 units along the y-axis road. On the other hand, if my roads are in the direction of 1, 1 and -1, 1, the same 5, 4 would have a different number, right? So it is something C1 times 1, 1 plus C2 times 1, -1. That's C1 and C2, right? So if I'm always going to measure things along these directions, then if I ask what is this matrix doing, it's just doing scaling in each of these directions. Such vectors are called as eigenvectors, basically, right? So they become easy because, of course, if you want to do computations, they become easy, right? So if you know diagonal matrix, you can take squares, you can take cubes, you can take whatever it is, you can solve any polynomial equations and so on. And that's why they are important to understand. Yeah.
Because essentially they are scaling. That's what it is.
Yes, every matrix is a scaling. In machine learning, all matrices just scale, right? So just that you have to look at it in the right direction. Just like PCA, right? So given the data set, it might be clumsy. If you look at it in the right directions, well, most of the information you can decorrelate the features and take the most important. It's as simple as that. Yeah. Okay, great. Anything else? Okay, so can you clarify assumptions used for KKT conditions? Okay, I don't think there are any assumptions used for KKT conditions. KKT conditions are just a set of conditions. Okay, by assumptions, if you mean, so these are conditions which are necessary for a particular point to be optimum for any constraint optimization problem. If you also want these conditions to be sufficient, right? So in the sense that if these conditions should characterize an optimum, then you need more assumptions about the functions and the constraints. They have to be, convex. If your function is convex, if your constraints are all convex, then KKT conditions are, both necessary and sufficient for optimality. Is that the question? Or
Sir, if possible, can you do an example for the KKT condition just as we did for height and weight, if possible? If possible, like on the whiteboard, if possible, just.
For the KKT condition, is it? Okay, so basic. Okay, So in some sense, if you have a convex optimization problem, right? So it is, again, all it is saying is that, so if you remember the Lagrange multiplier examples that I did, right? So where your gradients should, I don't know if you saw those lectures, right? So the gradient of the function and the objective should point in opposite direction. It's precisely a generalization of that, right? So your KKT is also doing only that, right? It's still saying that if you take the, the first order derivative of the Lagrangian, so that would be 0, which is essentially saying that your objective and the gradient at x star of your objective and your constraint should point in, like they should be anti-parallel to each other and so on. The only other extra thing that KKT would have is this complementary slackness condition. So I think the best example for that again comes from your support vector machine example, right? So which I don't think I can describe that in detail because so that need time. Okay, so but do you understand why the complementary slackness condition should be true, in the sense that you need the at optimality, the lambda star times the function's value at the primal optimal should be 0 for each of these, right? Is that clear? Because I mean, I think I did explain that in the videos. Is that kind of clear?
Right, because it needs to satisfy the constraint. Whatever constraint we have, it needs to satisfy the constraints. That's how the complementary slackness came into the picture.
Correct. So in some sense, it is just saying that if you have, so it at a very, very high level, it is saying that if you have a constraint set, your optimum is kind of going to occur at the boundary, right? So if it is, so a constraint of the sense of the form that h of x is less than or equal to 0, right? So which means that let's say h of x is, your constraint set is like a circle, and less than or equal to 0 means anything inside the circle. Now, so essentially it is saying that for most problems, you are going to get your solution in the boundary. Right? So unless the problem is kind of a degenerate problem. Why? Because in your boundary, you are going to satisfy it with equality, which means that your complementary slackness is automatically going to be solved. If not, if your optimum happens within inside, right? So if your optimal value happens to be inside the constraint, strictly inside the constraint region, so then what is that essentially saying? Well, that is essentially saying that your penalty is not really useful, right? So your lambda times you can think of your Lagrangian as kind of penalizing how far away you are in the constraint, right? So your penalty is not really useful because your optimum is already inside the constraint set. In some sense, then your lambda has to be 0, right? So that's the kind of, in some sense, a geometric intuition. But it's essentially, I think the way I will think of it is that it's kind of telling you that things happen, interesting things happen in the boundary, right? So that's the kind of intuition to that.
In real world, like I understand these models are these machine learning models are used tremendously in real life. Is there a simpler real life application that we can think of? Like just, okay, for this data set, support vector machine is the best. Like, is there something of that sort that you can think of right now, sir?
So if you had asked a machine learning expert 10 years before, they would have said for every data set, support vector machine is the best. Today, if you ask an expert, they would say for no data set, support vector machine is the best. You should always use deep learning, right? So things keep changing. If there were an answer to this, right? So then we would be teaching only one algorithm. Why teach the other algorithms? If there is only one best answer, right? There is no single answer. Because if I tell you that, hey, this algorithm is the best, then you can construct a data set that will fail, right? So in that sense, because it's a entirely data-driven thing, you cannot really say one algorithm is always the best. So now there are in practice, there are a lot of other considerations that come into picture. support vector machines have proved tremendously successful in face recognition kind of applications, even in e-commerce based applications. But if you really ask at least 10, 15 years before, when they were at the peak, support vector machines were at the peak, if you went to the top scientist at data scientist at Yahoo research, which was at that point like a very big thing, and asked them, are you really using support vector machines? They would say no. Right? So they would rather use even much simpler algorithms than support vector machines. Why? Because of scale. Right? So though the algorithm was amazing in terms of practical, in terms of these benchmark data sets, the real world calls for a lot of other factors. Right? So things like you want to do it as fast as possible. Maybe you are okay with 1 or 2% drop in accuracy, but then if you can solve in 2 minutes as opposed to 2 hours, you would rather do that, right? That's one thing. The other question is, I know there are people here who are in IBMs and other places, right? So if you take a solution to your manager and say, hey, this solution gives me 99% accuracy, the manager is always going to ask, explain what it is doing, right? So, and if you cannot explain really what the solution is doing, then, well, the manager is not going to be able to explain to his or her manager. And so most of these algorithms, these complicated algorithms, don't tend to get used because, at least in very mission critical applications, because they don't have a notion of how easy it is to explain. The more you complicate the model, the lesser the explainability of the models, right? So, and people prefer explainability to sound theory often, right? So, and so a lot of other algorithms that you will also see in the course, like for instance decision trees and things like that, which are very intuitive to explain, not necessarily always work the best, but still, from my experience, having worked in corporate for a while, people would say that, I would rather deploy something that I understand as opposed to something that gives me extra 2% accuracy now, but then tomorrow if it fails, maybe it's a self-driving car which has 98% accuracy, but then 2% you go ram into somebody and they die, right? So how do you? These are practical questions, right? So in fact, I think in 2015, Uber's self-driving car actually crashed a passenger and passenger died. And now who are you going to blame? Are you going to blame Uber or the person who wrote the algorithm or the person who approved this algorithm or who, right? So now you want algorithms that, this is another big area in machine learning today, right? So where you not only want algorithms that are very good in accuracy, but you also want algorithms that are explainable, right? So explainability is a big thing in machine learning today, right? So now, the reason why I'm saying all this is because the notion of best is often fuzzy because it depends on where you are using it, right? So maybe if it's your Facebook trying to find out if this face is you or your friend, then I don't care, right? So I don't really need an explanation. An algorithm might fail for a few of the participants, right? So maybe some people will not use Facebook, big deal, right? So 6 billion people, 3 billion people already use it. They don't mind losing a few people. But then if it is a mission critical application, then you need other things to take into account. So different algorithms might work better there, right? So it's a growing field. We still don't understand completely why some of the best algorithms today, state-of-the-art algorithms today, why they work. That's the first question you ask in any science, right? So why do things work, right? So we have already found things that work so well, but we don't know why. Right? So these are the algorithms called deep learning based algorithms, and as we speak, people are developing ideas and theories as to why these work. So all I can say is that there is no single best algorithm, and I hope, as you guys also learn about these things, you will develop some algorithm which fits the bill, right? So, and then we'll all close the area and say that we're done. We have the best algorithm that works, but yeah, that's not going to happen. Yeah. The short answer is there is no best algorithm. So it depends on the data that you have to try different things. Yeah.
Absolutely, got it. So, just one more thing, you mentioned about this idea of duality. It doesn't, this idea just came into my mind. I'm just treading on some variable land here. Can we think of PCA where we are minimizing the error and maximizing the variance as a dual problem? Is it somewhat related, or it's just an arrow fired blindly?
They are dual problems, definitely, right? So you can, but it is, in the case of PCA, it's more like not duality in the sense of the change of variables, right? So from so the duality of the type that we've seen in class, so they change from the number of variables that you're trying to optimize changes. In the Lagrange, your Lagrange multipliers become the variables that you are optimizing and so on. Whereas in the PCA case, it is just changing a maximization problem into a minimization problem. Just you put a minus and then it becomes a minimization problem. Right? So that's the Pythagoras thing, right? So you have variance squared plus error squared is your data points length, right? So, and now you either maximize this or minimize this, right? So it's like saying, again, there is one, I don't know if that was derived in class, but there is one derivation where you can actually see that in action, right? So you will either, you start from minimizing the error, writing your objective as minimizing the error. And then at some point you'll realize that if I write this, if you take this negative out and then write this as a maximization problem, it becomes maximizing variance, right? So it just, in that sense, it's just changing a minimization to maximization. The variables that you are optimizing are still the same. It's just that it becomes a minimum to maximum. Whereas the notion of duality that we are talking about are slightly more.
Right. The variables change. The variables change. Correct. Correct. So the example that we were given, we were asked to find the maximum profit. Maximum number of cakes to be sold or something of that sort, and to minimize the cost. So that's right. The variables are changing. Correct. Good.
Yeah, that's the important part. And so there are a lot of economics. I mean, the whole theory started in economics. So initially, I don't know if we are going about time, but anyway, yeah, people who have to leave, please feel free to. But I'll just make one comment and maybe finish this. Yeah, so this notion of duality, I think, started with problems in economics, where again you want to maximize, again, profit, and then you can think of this as a dual of minimizing resources, right? So these were the dual variables, and there the functions of interest were all linear, and the duality started. I mean, historically, people started looking at duality from a linear programming, linear functions point of view. Then they realized that the whole thing carries over to more interesting functions, which are convex functions and so on. But yeah, so I think John von Neumann, if you know him, so he's one of the father of duality theory itself, right? So and they developed something called as a simplex method, and we might have seen that in undergrad as some Tableau-based methods, right? So which nobody understood when we did undergrad why we're doing that, right? So that is just duality at work, essentially, for linear programs.
We are actually seeing that in our data structures course. That's also used.
Nice.
The concept of convex is used there.
I see. In data structures.
Yes. They want to optimize resources and a lot of. They want to optimize the time complexity in a lot of ways. So they are using linear programming. I haven't gone through the entire week, but I think Shreya has gone through it.
Yeah, I think it's leading to NP problems in algorithms. Yeah.
That's another fascinating notion, right? So
P and NP.
Yeah. So thankfully, we don't encounter too much of it in machine learning, because it's always, you're going to hit NP essentially when you have counting kind of problems, right? So when you have discrete things to optimize over. Here we always think of our things as RD, right? So anything in RD is okay. So typically our problems are not NP, with some notable exceptions actually. So again, you will see these when you talk about machine learning clustering based algorithms. One of the fundamental simplest clustering based algorithms called as the k-means clustering. You will encounter that later if you have not seen already. That can be seen as some kind of an approximation of the NP hardware and so on, right? So so there are other interesting there are interesting connections to kernel or the PCA I mentioned, right? So where you flip the AA transpose to A transpose A to clustering as well, right? So that's another interesting connection. One interesting clustering method called as the spectral clustering would come out of that. I don't know if that will again be covered, but yeah, so maybe you can note these things down, and after next semester you can look these things up, and then the dots will get connected better. Yeah. Good.
So one last question on projected gradient descent. I just wanted to know, like, when we do the projection, we'll hit the constraint, right? Like we'll find a y such that it satisfies the constraint. Now I know my function, I know the y. So why do I need further iterations? Can I not directly get that point where the function and the constraint are sort of intersecting?
No, what you do is in projected gradient descent, you are at some point in the search space. You're taking a gradient step. The gradient step is going to tell you the direction where the function decreases. The negative gradient step is going to tell you the direction where the function decreases. But that direction need not be the direction where the constraint is also satisfied. Right? So if you move in that direction, you might actually decrease the function, but your function may not be satisfied. So what you do is you again project it back to a point in the search space where your constraint is satisfied. Right? So now why would this be enough? Right? So this is like one gradient step in gradient descent. Right? So you've just moved a little bit, just that you have made sure that you are still satisfying the constraint. Now again, so it is like climbing a hill, but then you are making sure that you are in some region of the space, right? So I didn't understand the question.
Can I just explain it to you with a picture I have in mind? So if I think of something like a bell as the function, and if there is a cylindrical constraint at some point, now the cylinder is the constraint. So in the bell, I can't go completely towards the trough, right? Because the constraint is the cylinder. I need to stop where the cylinder intersects the bell to find the lowest point. Now, what I'm saying is in one iteration, I may move beyond that point where the cylinder acts as a barrier. So I'll project the point back to the cylinder. So now I have that point and I have the function itself. So can I not find the point where the two are intersecting each other? Why do I need further iterations? Like I already know that those 2 points, right?
So you're talking in one dimension, right? So let's say the cylinder was big enough that it encompasses the whole bell.
Okay.
Now what do you do? Now if you take one gradient step, that's not enough anymore, right? So you have to keep taking gradient steps to reach the minimum, isn't it?
Okay, so you're saying it can be within the cylinder, so I may need to come back.
You have to come back. So what I'm saying is that all we are saying is that the problems with gradient descent are still going to not go away, right? So your gradient descent is not going to give you an answer in one step, right? So it will give you an answer in one step only if you can solve the gradient equation and set it to 0 and solve that analytically, which is something that we cannot do, and hence we are resorting to this steps iterative solution. Right, so it's the same type of problems that we want to solve here as well. Right, so you cannot take the gradient, set it to 0 and solve it. Here you won't set it to 0 because that may not satisfy your solution, which means you cannot even project it back. Right, so you cannot solve those problems. So we still have the same problem as gradient descent, and so we are taking this gradient step. All we are saying is that at every step, bring it back to the projection, the area where your constraint is satisfied. But that does not necessarily mean that after making that projection, you have solved the problem. right? So you have just made one step in the correct direction. You still have to make more steps, right? So that's the idea. I think the one-dimensional thing might be misleading, but if you think of it as like a higher dimension, I think then you will see that just making this projection does not solve the problem. And never solves the problem. Yeah.
Got it. Yeah. Nice.
Okay. Yeah. So we are over time, but yeah. So if there are any final thoughts, comments, anything, we can discuss now.
Sir, I just have one suggestion. Like, if possible, in the next term, whosoever are my juniors, if you could provide us some actual coding-based things where we can apply PCA, apply SVD, apply optimization, and observe it ourselves, like a assignment sort of stuff. That would be very helpful to all the students, because right now, I mean, we understand the intuition, we understand the math, but when we actually apply it, we find the glow and we understand it thoroughly. So
absolutely, if you don't apply, it's yeah, so it takes time to get that abstract level of thinking, right? So it's always good to get your hands dirty. Yeah, so we will. So I don't know if there's going to be a final feedback form that is going to be circulated. If not, I request the TAs to do that. Where please be candid, give all your feedbacks, what you think can be improved, what you think did not go well this time, right? So because we want to, we will strive to make it better. So we will strive to make it better next time, right? So please do that. I mean, this is a valid feedback. We will take this. You will see these things, I'm sure, in the machine learning practicals course next semester anyway. But I mean, nothing wrong in doing it now only, right? So yeah, we will take this as a feedback. Thanks. Okay, so
thank you so much, sir. This was a wonderful interactive.
Thank you, sir.
thank you very much, sir. It was very insightful for all of us.
Yes, sir. Because somewhere in learning the rigorous math, we forget the intuition, why we are doing this. So such type of sessions are very helpful. So maybe next time more such session 2, 3 maybe will be held.
Sure, we'll do that next time. Thanks for the feedback. Okay, thanks everyone, and all the best for your exams and for the upcoming
Thank
semester.
you, sir, for your
Thank you, sir.
enlightening and enjoyable session. And thanks a lot for participants. You encourage us a lot.
Yes, sir. Thank you so much, sir. It was really an informative session for me as well. Thank you so much, sir.
Thank you. See you all. Have a good night. Bye.
Bye, sir. So, bye, everyone.
Bye, everyone.
Bye.
Bye, everyone.
Good night.
Thank you for your participation, all of you.
Thank you to all the TAs for always keeping a very good session.
Yeah,
We will see you soon. Bye.
Bye.
Okay. Bye, all.
Bye, ma'am.
Abhinandan, actually, Srinivasan sir has sent. Okay, he just said bye. Okay.
He left.
Okay. Okay. Bye, Abhinandan. Bye, Jimmy.